We present JointDiff, Bridging Continuous and Discrete in Multi-Agent Trajectory Generation, published at ICLR 2026, a collaboration between Cognia Sports Intelligence, EPFL, and the IRIU-PC Barcelona. In team sports, a scene is described by two tightly coupled modalities. First, continuous trajectories, the XY coordinates of players and the ball over time, and second, discrete events, like which player possesses the ball at each time step. Current approaches model only the continuous trajectories and overlook these discrete events. This leads to physically implausible generations, for example, unrealistic passes or incorrect ball possessor interactions. Our insight is to model both modalities jointly. Because ball movement and possession are fundamentally linked, the ball changes direction when possession changes. Joint modeling produces more realistic and controllable generation. JointDiff is a joint continuous discrete diffusion framework. The forward process operates independently on each modality. We add Gaussian noise to the continuous trajectories and uniform categorical noise to the discrete possession events. The key is in the reverse process, which is joint. Both the continuous and the discrete heads are conditioned on the full noisy state, trajectories, and events together. This shared conditioning is what allows the model to learn the cross-modal dependencies between motion and possession. Here is the denoiser architecture. The model takes as input the noisy joint state, the observed conditioning states, a binary mask, and an optional guidance signal, either a possessor sequence or a text description encoded through a frozen T5 encoder. The network processes these through two social temporal blocks and outputs two predictions: a continuous head that predicts the injected Gaussian noise on trajectory coordinates, and a discrete head that predicts the possession event probabilities. To enable controllable generation, we introduce CrossGuide, a cross-attention module placed inside each social temporal block. We support two guidance modalities. Weak Possessor Guidance, or WPG, lets users specify a simple list of intended ball possessors. The guidance is encoded through learnable agent embeddings and cross-attended with the ball's hidden state only. Text guidance provides finer-grained control through natural language descriptions. Here, a frozen T5 encoder produces text embeddings, and every agent independently cross-attends to the shared text context. We first evaluate on completion tasks like future generation and imputation, with no guidance or control applied. Here we show results for future generation. We report scene ADE, which averages the displacement error across all agents in the scene rather than per individual, better capturing multi-agent coherence. Starting with the best of 20, this metric naturally favors non-IID methods like MART and MoFlow, which generate correlated modes in a single forward pass. Even so, JointDiff remains competitive across all three datasets. But the full picture emerges when we add the average metric. JointDiff consistently achieves the lowest average SAD across NFL, Bundesliga, and NBA, outperforming all baselines. This reflects higher distributional fidelity. Every sampled mode is realistic, not just the best one. For controllable generation, we compare our full joint model against a variant without joint modeling, one that only optimizes continuous trajectories. Each chart shows three settings: no guidance, weak possessor guidance, and text guidance. The improvements are consistent across all datasets and all guidance modes, ranging from 3 to 9%. The largest gains come with text guidance, confirming that richer semantic conditioning benefits the most from jointly modeling trajectories and events. So, what does our joint diffusion approach achieve? First, it generates multi-agent realistic data. Here is a qualitative comparison on NFL future generation. Given past observations shown in white, we compare MoFlow, U2Diff, and JointDiff. Notice how our method produces tighter, more coherent player formations and more plausible ball trajectories. Second, it generates diverse plausible scenarios. Here we show 5 independently sampled modes on the same NBA scene. The top row is JointDiff, the bottom row is MoFlow. Our model produces genuinely diverse and realistic futures. Each mode captures different player interactions and ball trajectories. MoFlow, in contrast, achieves diversity by partitioning the court into zones. Each mode covers a different region, rather than generating tactically varied plays within the same area. And third, it enables controlled outcomes. Here is an example of text-guided generation on a Bundesliga scene. The text prompt specifies that player 16 possesses the ball at left center, moves it downside, then passes to player 21, who passes to player 19 into the box. On the left, the model without joint training fails to follow this sequence. On the right, our full JointDiff model correctly routes the ball through the specified players and locations. To summarize, our joint diffusion approach generates multi-agent realistic data, diverse plausible scenarios, and controlled outcomes. Thank you for your attention. Come visit our poster or check the project page for more animated results and to download our datasets.